Okay, so in the last section, we took a look at a sphere of radius r with a magnetization m in the z direction. It was constant. And we asked what was the dipole moment of the sphere, and we calculated it two different ways, winding up with the result, not surprisingly, that it was just the volume of the sphere multiplied by the magnetic moment per unit volume m. That was our result. And at the end of that section, I said that would be instructive for you to calculate the magnetic field of the sphere. So let's draw a little sphere here, far away from the sphere, so we know it's going to produce a dipole field. And I said that it would be useful for you to go and calculate that quantity, and that you should do it, and that I wasn't going to do it, but I've changed my mind. I am going to do that for you, and the reason is that it's a fairly good little exercise in vector calculus, so I thought I'd show you how to do it, and then you can try it on your own. Okay, so our starting point is going to be our formula for the dipole term in the vector potential. Okay, so this is our starting point, and of course m is given by this quantity here, and furthermore we're going to put m at the origin, so r prime is going to be 0, and this vector here will just become r hat, and the mod here will just become, this is just going to be r squared. So we wind up then with the following expression for a. Okay, so there's our expression for A, and really the only bit of work we're going to have to do is we're going to have to take this cross product, z hat cross r hat, and you'll remember that this cropped up in the previous calculation as well, and I suggested you should convince yourself that you know how to do this. I thought it might be useful really to show you this. This is really why I'm doing this calculation, just to make sure you know how to take this cross product. These crop up a lot in vector calculus, and you need to be quite familiar with how to change basis in order to take a cross product of this kind. So let's do that now. Okay, so in order to do this, we're going to express the z hat unit vector in terms of the spherical unit vectors. Okay, so this is really the key step. We've expressed z hat in terms of r hat and theta hat. And if you're in any doubt about how to do that, you need to come and talk to a tutor or talk to one of the lecturers to ensure you know why that is so and how to do that kind of calculation. Having expressed it in this form, the cross product is straightforward to do. Alright, so when you look at this cross product, the cross product of r with itself is 0. The cross product of theta hat with r hat is phi hat. This is from the right hand rule. If that doesn't make sense to you, you need to come and talk to us. And so we pick up this sine theta phi hat term. So when we substitute that cross product back into our expression for the dipole potential, we get the following result. Okay, so to complete our calculation of the magnetic field well distant from the sphere, all we need to do now is to calculate the curl of the vector potential, but we need to do this in spherical coordinates. So let's write down all the components in spherical coordinates and have a look at how we complete this calculation. Alright, so this is curl in spherical coordinates. I hope I've got all those components correct. I think I have. And it's a fairly ugly looking expression, but most of the terms in here are zero. So you remember the only non-zero term in our expression for the vector potential, A, was the A phi term. There was only a component in the phi hat direction. So that means all A theta terms and AR terms are zero. So let's get rid of those. There's an A theta, AR, AR, and we're left only with two terms. We're left with this term here, which is going to give us an R hat component, and we're left with this term here, which is going to give us a theta hat component. And you can go and complete the two derivatives. Those are straightforward to do, and when you do that, you'll get the following result. Okay, and that completes our calculation. Now, we did this for a sphere of radius r and magnetization m, magnetic moment per unit volume m. But of course, this is true of any dipole, so it's a pretty generic dipole calculation. But I thought it was useful to show you how that basis change worked, and also to show you how to take the curl in spherical coordinates.